Let's do section 9.4, exploration 1, investigation of the integral from 0 to 1 of dx over x to the p. Number 1, explain why these integrals are improper if p is greater than 0. Well, if p is going to be greater than 0 or positive, that tells us that x to the p is going to stay in the denominator. So we're going to have 1 over x to the p. And because of our limits of integration, that means at some point we're going to have 1 over 0 to some power. And that is, of course, going to go to infinity. So this is going to lead to an infinite discontinuity at x is equal to 0. And that's what's going to make these integrals improper if p is greater than 0. So number 2 says, show that the integral diverges if p is equal to 1. So that's going to give us the integral from 0 to 1 of 1 over x dx. And as we said, this is an improper integral, so we need to change this into a limit as a approaches 0 from the positive side of the integral from a to 1 of 1 over x dx. And we know what the antiderivative of 1 over x dx is. So this is going to give us the limit as a goes to 0 from the positive side of the natural log of x evaluated from a to 1. And now we're ready to substitute in our limits of integration. So we're still going to have our limit as a goes to 0 from the positive side. And we're going to have the natural log of 1 minus the natural log of a. And of course, the natural log of 1 is going to be equal to 0. But as we apply that limit as a goes to 0 from the positive side, this is going to give us the natural log of 0, which is going to go to infinity, which means that our integral is going to diverge. Part 3 says, show that the integral diverges if p is greater than 1. So again, we're going to have our integral from 0 to 1 of 1 over x to the p dx. Again, because of our infinite discontinuity at 0, this is an improper integral, and we're going to have to introduce a limit as a goes to 0, again from the positive side, because we're looking at that integral from 0 to 1, interval from 0 to 1. And this is going to be my integral from a to 1 of x to the negative p dx. And I can find the antiderivative of this kind of using that inverse power rule. So this is going to give me the limit as a goes to 0 from the positive side of x to the negative p plus 1 divided by negative p plus 1 evaluated between a and 1. So again, we're ready to substitute in our limits of integration. So I'm going to have the limit as a goes to 0 from the positive sign. I'm going to pull out the constant, so that's going to give me 1 over 1 minus p. And I'm going to have 1 to the 1 minus p. And then I'm going to subtract a to the 1 minus p. Well, if p is going to be greater than 1, then 1 minus p is going to be less than 0. And that means that this factor here is going to go to the denominator. And if it's going to be in the denominator, I'm going to get something that looks like this. The limit as a goes to 0 from the positive side of 1 over 1 minus p times 1 minus 1 over a to the absolute value of 1 minus p. And if I'm doing that, then as I plug in my limit as a goes to 0 from the positive side, this is going to go to infinity. So my whole integral goes to infinity, and that means that it diverges. So number 4 says, show that the integral converges if 0 is less than p is less than 1. So we've got our integral from 0 to 1 of 1 over x to the p dx. And this is still an improper integral, so we're going to have to introduce that limit again. So we're going to have the limit as a goes to 0 from the positive side of the integral from a to 1 of x to the minus p dx. And we can find the antiderivative of this, and we're going to have the limit as a goes to 0 from the positive side of x to the negative p plus 1 divided by negative p plus 1, evaluated from a to 1. And now, if 0 is less than p is less than 1, then this means that negative p plus 1 is going to be greater than 0. And this means that x to the negative p plus 1 is going to stay in the numerator. So I'm going to rewrite it using absolute values. So I'm going to have the limit as a goes to 0 from the positive side of x to the absolute value of negative p plus 1 divided by negative p plus 1. And I'm still going to evaluate this from a to 1. And now I'm ready to substitute in my limits of integration. So I'm going to have the limit as a goes to 0 from the positive side. I'm going to pull out that 1 over 1 minus p, and then I'm going to have 1 to the negative p plus 1 minus a to the negative p plus 1, and those are absolute values on those exponents. And now, when I substitute in for my limit as a goes to 0, this is going to go to 0, but it doesn't really matter because it's in the numerator. So this integral is going to go to 1 over 1 minus p, and because it's equal to an actual number, depending on what p is between 0 and 1, that tells me that this integral is going to converge. And all of this should look familiar because it's very similar to the p-series that we talked about in Chapter 10.